In this section, we are going to learn derivatives and integrals of vector functions. In the previous section, we learned vector functions. Vector functions, first of all, is a vector. Second is a function of t. Since it's a vector, so they have three components: ft, g sub t, and h of t. The graph of the vector function is a curve. Just like a scalar function, for the vector functions we can define its limit, derivatives, and integrals. First, let's see the definition for the limit for a given vector function, which is pretty easy. Okay, what you need to do, just find the limit of each component. Then you find the limit of the vector functions. T goes to a g sub t, and the limit t goes to a h of t. So the limit of a vector function r sub t as a result is a vector with three components. Similarly, we can define the derivative. Also has been defined component-wise. F prime t, you take a derivative of each component. Okay, so the derivative of a vector function as a result is another vector function. Also, we can define the integral of a vector function. Again, has been defined component-wise. So what you need to do is integrate it, each component. So remember, the integral of a vector function is another vector function, is a vector. Okay, so to find limit of derivatives or integral for a given vector function is pretty simple. What do you need to do? Just perform whatever the operations, just component-wise, you are done. However, if the RT there is a vector, okay, and we know this one is the graph of that is a curve, and RT is a position function like this. Okay. Then what about R prime t is a derivative, is another vector. Okay. In fact, this vector is give you the tangent. Okay. This is RT. Then this tangent direction is another vector, is R prime t. R prime t. Okay, we give a unit tangent vector, we give a special name, we call capital T. Capital T is unit vector of RT divided by its own magnitude. So remember, capital T is a vector. This vector is a tangent, give you tangent direction, but at the same time its magnitude is 1. Now let's look at it. Let's look at the example. Now I give you a vector function. RT equals square root of t I plus 2 minus t j. If you write in the component wise, it's like square root of t 2 minus t. So since we have two components, so this is a plane curve. It's a curve just like on a plane. Okay. Now, what do we want to find for this plane curve? We want to find r prime of t, and also we want to sketch two vectors. One is r position function itself, 1t equal to 1, and r prime evaluate 1t equal to 1. Okay, this is a plane curve. Now, do we know how to sketch this curve? Now we means here's x and here's a y. Okay. In the other words, this plane curve, x can be found by using formula square root of t, and the y is calculated by 2 minus t. Okay. So for given t, you can find x, y. For given different t, you got a different x, y, then you got a curve. Okay. So what kind of curve is that? Remember in the previous section I told you for the plane curve, we can get rid of t and end up relationship between x and y, which is we know better in that form. Okay. So if we take square on both sides, we got t equal to x squared. Therefore, your y equal to 2 minus t, which is x squared. So this curve described by this parametric form really is a parabola, like this. Okay, what is R1? R1, just like R there, replace t by 1. So if here replace t by 1, you got square root of 1 give you 1. Then replace t by 1, 2 minus 1 give you another 1. So that is a vector start as the origin and end up with a point 1, 1. So that's what that vector is. So this vector is RT, R1. Okay, then what is R prime 1? R prime 1 is, okay, we have to find the derivative first. Okay, we need to find R prime t first. For given vector function, how do you find its derivative? You just need to take a derivative of each component. Okay. So first, let's take the derivative for square root of t, give you 1/2, and the t 1/2 minus 1, give you minus 1/2. Then take derivative of second component, give you minus 1. Okay, so that's give you r prime t. So take a derivative of vector function is pretty simple. You just need to find the derivative for each component. Okay. If you want to find r prime 1, you just need to replace t by 1, which give you 1/2. T is 1, then negative 1/2 root still give you 1, then minus 1. Okay. So what is the vector r prime 1? That's a vector, say x is 1/2, y is minus 1, something like this. Remember, the vector will be, two vectors will be same. They have same magnitude and the same direction. Doesn't matter which point they start with. So this vector is r prime 1, and this one same thing. Okay. R prime 1. So you can see this is a tangent. Give you the tangent direction at that curve. Okay, now let's look at another example. Now this example we want to find parametric form. Parametric equation for the tangent line. To the curve, this curve has been given by this parametric form. X equal to 2 cosine t, y equal to 2 sine t, and z equal to 4 cosine 2t. Okay. If this one, if you want to write as a vector function, it's like this. The first component is 2 cosine t, second is 2 sine t, and your z there's a 4 cosine 2t. Okay, now I give you either this one parametric form or this vector form. The same thing. It's a graph, is a curve, okay, in the space. Now what we want to find is a tangent line to this curve. If you want to find a tangent line, you have to tell me which point. They tell us we want to find the equation of tangent line to this curve at a point square root of 3, 1, and 2. Okay. So say this point is square root of 3, 1, and 2. Now we want to find the equation for the tangent line. Okay, recall, to find the equation of a tangent line, you need to know P0, right? One point on the line, which is easy to find. Square root of 3, 1, and 2. We know this point on the line. Okay. And another thing we need to find n, right? N is a vector your line parallel with. Okay. So how do we find n for this case? We know we give you a curve r, function r. Now if you take a derivative, that would give you tangent direction, right? That will give you the n. Okay. R prime t will give you the tangent. So we need to find the derivative first. Okay, now let's find the derivative. Find the derivative for vector function. Just find the derivative for each component. So give you 2 sine t. Then the second one give you 2 cosine t. The third one give you 4, take the derivative of cosine 2t, give you negative, then give you negative sine 2t, then times 2. So you got this 8 sine 2t. Okay, what is this? This is a tangent direction at a t. Now we want to find the tangent direction at this specific point. So we need to know when t equal to what? Give you this point. Okay. Now we know we want to find the t such that we want to find the t such that 2 cosine t give you square root of 3, 2 sine t give you 1, 4 cosine 2t give you 2. So obviously, you solve here, you say cosine t equal to square root of 3 over 2. Sine t equal to 1/2. So from here we know t must be pi over 6, or you say 30 degrees. Therefore, your n can be found by tangent direction, which is r prime t. Take t equal to pi over 6. Because at a different t, your tangent will be different. So you just go to the r prime t, replace t by pi over 6. So you get negative 2 sine pi over 6, then 2 cosine pi over 6, then negative 8 sine 2 pi over 6, which give you negative sine pi over 6 give you 1/2, so give you negative 1. This one give you square root of 3 over 2, so give you square root of 3. Then 2 times pi over 6 give you pi over 3, which give you square root of 3 over 2. Times that give you minus 4 square root of 3, right? Okay, that's your n. Okay. So by knowing n and p0, we can find equation of a tangent line. Remember, is x0 plus at, y equal to y0 plus bt, z equal to z0 plus ct. For our case, our a here is square root of 3, right? Plus at. A is minus 1 times t. B there is 1. Y0 is 1 plus bt. B is the square root of 3 times t. Z0 is 2. Then plus c times t. C is minus 4 square root of 3 times t. So we find the parametric form for line. This line is a tangent line for the given curve at the given point. Okay. So line is a special curve.